Hi, my name is Anna Volker, and today I'll be telling you the story of humanity's connection to the cosmos, tracing our ever-evolving understanding of the universe through the ages. From the ancient Egyptians, to the revelations of Copernicus, to Einstein's biggest blunder, to the revolutionary discovery of gravitational waves, and to modern mysteries we still have yet to unravel, tonight we will explore and experience the universe through the unique lens of history. I'm going to go to the back now to fly the show, but I thank you all for being here, and I'd like to remind you to please turn off your cell phones, and we'll be ready to begin the show. We're going to begin our journey starting about 5,000 years ago in ancient Egypt. Astronomy influenced many aspects of Egyptian life, impacting everything from agriculture to architecture. They took detailed records of the sky and made connections between the celestial patterns and their calendar of celebrations. Many temples were actually built in relation to the stars and to the constellations that they observed, and some of these temples even had the observations of the night sky carved into their ceilings, mixing astronomy and art together. But perhaps the most intriguing aspect of astronomical Egyptian life was the pyramids. Now, the pyramids are one of the 7 wonders of the world, and out of all of these wonders, they are the only ones still standing today. The pyramids of Giza were built as monumental tombs for royalty, and if we take a closer look at their structure, we find that they're actually built aligned to the stars. So if we go here to look at our night sky, we can see that the pyramids have what we call air shafts, and these led from the chambers inside the pyramids to the outer walls. Many thought these were intended as passages through which the ruler's soul was thought to spiritually travel. One of these passages, coming from the king's chamber, pointed directly at Orion, seen here in red. Interestingly enough, Orion was associated with the god Osiris, depicted here on the left. Osiris was the god of death and lord of the underworld. If we look at the queen's chamber, we find that there's also an air shaft, and this one is directly aligned to point at Sirius, the brightest star in the sky. Sirius was associated with Osiris's sister/wife, Isis. Isis is seen here on the right, and Sirius is that star right there in the center that we're circling in yellow. Many people thought that the Nile was flooding every year because of Sirius. So we're zooming in here on Sirius, and what happened was this star appeared in the night sky every year, coincidentally, before the Nile flooded. And so many thought Isis was crying for the death of Osiris, and it was her tears that flooded the Nile, which was an extremely important part of Egyptian life because it marked the new beginning of a crop season. However, the Egyptians weren't the only ones to find meaning in the stars. This was a very common phenomenon, and if we look to ancient Mayan culture, we find that astronomy provided a link between the mortal and the immortal. The Milky Way, the galaxy in which we live, can see as a bright band of light across the sky. This glowing path depicted here was called the Road of Souls and was thought to lead the dead to the underworld. So what we're actually seeing when we look up into the sky and are lucky enough to see our Milky Way is the edge of our galaxy. So we're inside this galaxy and we're looking out to that distance, edge on, from our unique inside perspective. So think about the Milky Way as just a flat pancake and we're inside looking out. However, today, abundances of light obstruct our view of the night sky. So many of us, myself included, have never really gotten the chance to see the Milky Way in its full glory. So this is called light pollution, as you can see here what we're simulating with our cove lights. And that's why we can't go outside right now and see this beautiful band of light. However, back in 1800 BC, it's shown as this clear path of light across the sky because there wasn't this light pollution to interfere with our view of the stars. But as we know, light comes from more than just stars in our Milky Way. We observe light from a variety of objects, such as comets, like you see here. Now, comets are essentially just dirty snowballs of solidified gas, dust, ice, and rock that are orbiting our sun. The Mayan referred to them as stars that smoke, and they viewed them as an omen of death for people of nobility. Moving forwards in time, we still see humanity's tendency connect these astronomical phenomena we're observing to events happening here on Earth. In 1066, for example, Halley's Comet appeared in the night sky. And so here we see our sun, and we're going to now look at Halley's Comet. Its path is traced out in yellow, and around it in blue is the path of our own Earth around the sun. Now, notice how much bigger Halley's path is. If we look at this yellow path, we see that it's a long, elongated ellipse. This is because comets have very eccentric orbits, meaning they're very squished and elliptical, and it can mean they take a very long time to orbit around our sun, much longer than our own Earth. Halley's Comet, for example, has a period of 76 years. And if we zoom in here, we can see a closer look. So what we did now, we zoomed right into the comet's path, which is pretty interesting because meteor showers are actually the result of the Earth passing through the orbit and leftover dust trail of a comet. So these dust particles are burning up in our atmosphere, and they create the bright streaks that streak across the sky that we call shooting stars. The average size of a shooting star is actually no bigger than the tip of your pinky finger, so the fact that we can even see them at all is a testament to how bright they really are. Fascinatingly enough, when this comet appeared back in 1066, it was seen as a sign that King Harold of England would soon die, and later that same year, he actually was killed in the Battle of Hastings, so that furthered these superstitious beliefs people were holding on to. And we see moving forward in time still that these superstitions continue to persist throughout culture. For example, in 1572, even more fuel for these beliefs and superstitions arose when a new light appeared in the sky. So here in red, we see the constellation of Cassiopeia, and around this time, a new light appeared right there just above the constellation. Now, this really shook our understanding of the constellations and the stars, because at the time, it was thought that the sky should be unchanging, so they didn't expect any new lights to appear. Astronomer Tycho Brahe discovered this new star in the constellation, and he published De Nova Stella, giving rise to the term supernova. We now know that this wasn't actually a new star at all, but rather the result of an incredibly powerful explosion that can occur when a massive star reaches the end of its life. So these massive explosions, called supernovae, happen when a star is too big to hold itself up and it collapses due to the force of gravity pushing in. So here on the left, we have a white dwarf, a very small, compact, dead star, and it's pooling gas off of its partner, which is a large red giant. So these stars orbiting each other are what's called a binary system. They're going around one another, and the white dwarf is pooling gas onto itself, getting bigger and bigger, but eventually it can no longer hold itself up, and it can't support itself against the gravity of its own mass, and it explodes in what's called a Type 1a supernova. The beautiful thing about these explosions is that they scatter elements all throughout the cosmos. So new elements can be created in them, but also what was making up the interior of those stars gets scattered everywhere. So the bellies of these massive stars actually get reused and recycled to form our bodies, our solar system, everything around us. So we're actually made up, literally, of star stuff. Now, what you're looking at here are the remnants of this very supernova that Tycho observed in 1572. So this is an actual picture of the supernova remains taken with a modern telescope. Almost as fascinating as this discovery was the man who made it. Tycho had a disagreement, for example, over a mathematical formula once, so he decided to settle it in a sensible and mature way by getting drunk and having a sword fight in the dark. Now, as you can imagine, this did not go all that well for poor old Tycho, and he ends up losing his nose in the duel, and he spent the rest of his life allegedly wearing a nose made out of silver and gold. In China, this new star was also seen and recorded, and in fact, the Chinese have been recording supernovae ever since they had writing. Much like the Mayan view of comets, this unexplained light was seen as a sign of evil for the Ming Dynasty's emperor. So we still see this idea of astronomical activity meaning foreboding omens for the people in power. So when we don't understand these unexplained lights, people have a tendency to associate them with death and with fear. This new discovery of the star was important also because it challenged this Aristotelian view of a fixed celestial realm. So that just means, like I mentioned earlier, that the classic view was that nothing should ever change in our sky. So with new lights appearing, we had to start rethinking everything we thought we knew. And this brings us to our evolving understanding of our own solar system's structure. At the center of this system, for a very long time, we wanted to place our own Earth. So that's what you see here, and it's called the geocentric model. The Earth is at the center. But what's the first thing you notice about this model? Something very strange is happening here, right? We're seeing these complex loops that each planet is tracing out. These loops are called epicycles, and they were thought of by early astronomers to explain the complex planetary motions that they were observing. So, while this model was wildly incorrect, as we now know, it's important to acknowledge how sophisticated and mathematically complex it really was. This model was based on real observations of how the planets wandered around the sky, which is where we get the term planet, coming from the Greek word for wanderer. So now we're seeing this shift from mythology and superstition to real scientific data. So we're still driven by our curiosity and our need to understand the universe around us, but we're now relying on observations rather than assumptions. So we now know that this can all be easily explained, and we don't need these epicycles if we just use the heliocentric model. So if we place our sun at the center, that's our current understanding of our solar system, and we now know this is the way it looks, and the Earth is in fact revolving around the sun, not the other way around. This heliocentric theory was first published by Copernicus in 1543. And almost 100 years later, in 1633, Galileo comes out in support of this theory, but he's actually imprisoned when the Roman Inquisition finds him vehemently suspect of heresy. So almost 100 years go by after Copernicus proposes this theory, and people are still getting imprisoned for it. There's this consistent reluctance to accept change, whether that's change in the sky or in our understanding of it. But I think it's pretty interesting to note that Copernicus wasn't the first guy to put the sun at the center. This idea of the Earth revolving around the sun, and not the other way around, was actually first introduced all the way back in 2080 BC by Aristarchus. So over the next few hundred years, we now start to map out our known universe, discovering thousands of stars in our own galactic neighborhood. But this entire time, we still think our universe is relatively small and unchanging. As we enter the 20th century, this view of the universe is quickly shattered as our understanding becomes revolutionized. At the front of this revolution was a man named Albert Einstein. Albert Einstein completely transformed our view of gravity and the so-called empty space between our planets, stars, and galaxies. So Einstein comes up with the general theory of relativity, and he proposes that space and time are actually woven together into a fabric known as space-time. So now I'd like to demonstrate a little bit about what Einstein was talking about. So space-time, we can model here, we have a nice yellow fabric I'm coming down to, and the idea was that when you put mass in space-time, space-time bends around this mass and is distorted by the objects in it. So when I say mass, we're just talking about anything with stuff. So that's you, that's me, and that can even be our sun, which we're going to model here with this nice heavy weights. So when you put the sun in the center of our space-time fabric, you notice it dips down, so we create these large distortions in the area around it. And this is what gives way to what we call gravity, because what happens is other objects follow the distortion caused by mass and the space-time that bends around it. So if we take our Earth, for example, we see that it orbits around the sun and is following this curvature. And so this is what Einstein was trying to explain with gravity. It wasn't some magical, mysterious force we couldn't understand, but actually something we could easily explain by using this model of space-time and looking at the ways that objects with mass can distort it. And the more mass something has, notice the sun has more mass than the Earth, the deeper the distortions in space-time. And that's why our heliocentric model makes sense. Our sun has more mass, so that's what the Earth is orbiting and not the other way around. So this was a brand new idea and really started a revolution in our understanding of gravity and how things actually interact with one another. We now have a better understanding of how space works. but we still don't really know how big space is until the early 1920s. At this time, a man named Edwin Hubble came onto the scene and started really making us understand how big our universe really is. In 1923, Hubble makes the striking realization that what was then called the Andromeda Nebula is actually much, much more than that. So at the time, it was thought to be just a simple nebula, which is just an enormous cloud of dust and gas that often double a stellar nurseries. So here we see Andromeda, and we're zooming in here. We're finding that it's not just a nebula, but actually its very own separate galaxy. So we can zoom in here and see the Andromeda galaxy in its full glory. And here we have it. So this Andromeda galaxy is actually millions of light years away, far, far beyond the boundary of our own galaxy. He used a method pioneered by Henrietta Leavitt to measure the distance to this so-called nebula and found out that it's not a nebula at all, but rather its own island universe, a separate galaxy with billions upon billions of stars of its own. This made the universe really grow to epic proportions because we truly discovered how big our universe really was that day. So to even understand this further, we're now going to look at the furthest reaches of the cosmos that we have yet to observe. And that'll help us really understand how big our universe is, at least how big we know it to be at the moment. So here we are at Earth. So we're going to begin our journey at our home, quickly zoom away. We see the moon's orbit around our own Earth. We see our Earth's orbit around our own sun, and now we're leaving our solar system behind as we fly through the Milky Way galaxy. Notice that the rate we're moving at right now is much faster than the speed of light, which isn't possible in real life. The speed of light is our cosmic speed limit. You can't go faster, but here we're quickly zooming out of our own galaxy. You can see this bright band of light forming in the background. That's the Milky Way, and we're zooming across it much faster than light, which would take 100,000 years to travel across it. But here we leave it behind, and we see our galactic neighbors. That's our local group of galaxies. Further and further out still, we see more and more galaxies starting to form our understanding of what the universe looks like. And here we have it. This is our biggest view of the universe today. So each point here is not a star, but rather its own separate galaxy, billions upon billions of stars. And note these gaps don't indicate no stars and no galaxies there, but rather it shows what we still have yet to explore. So there's all this area we still don't fully understand, and so more to discover still to this very day. So Hubble didn't just show us more galaxies were out there, he actually looked at how these galaxies moved. And what he found was each galaxy was moving further and further away from us. So this implied that the universe is actually expanding. A way to imagine this is if you have a loaf of raisin bread. If each raisin in that bread is its own galaxy, and as the bread expands, the distance between each raisin will get bigger and bigger. So that's what we're seeing here, sort of like an expanding balloon, if you will. And the universe grows and grows, and as it does so, the galaxies move further and further away from each other. And that's what Hubble realized, which we had no idea was happening until this point in time. And if that wasn't amazing enough, later, in 1998, we discovered that not only is our universe expanding, but it's doing so at an accelerating rate. This is due to a mysterious force we've dubbed dark energy. When astronomers don't really understand something, we often throw the word dark in there to indicate we don't really know what's happening, but we know it's there, and we know it is fascinating. What we understand about dark energy is that it's responsible for the acceleration of the expansion of our universe. That means everything is getting further away from everything else at a faster and faster pace. We also know that this dark energy makes up about 73% of our entire universe. So that's a huge portion of our universe that we completely do not understand to this day. Interestingly, Albert Einstein had predicted that we live in a static universe. He didn't think there was expansion at all. He just thought that there should be no movement in the universe's size, and it stayed static. In order for this math to work out, his equations featured a cosmological constant. Essentially, a constant in his equation, just a number, that counteracted the force of gravity. When he discovered that the universe is expanding, or rather, when he was told of this discovery, he was extremely embarrassed and called this cosmological constant the biggest blunder of his life. However, even though his views of the universe were wrong, his calculations for determining this factor that acts in opposition to gravity were spot on. So while he wasn't applying it correctly and didn't understand that the universe was expanding, he correctly described the behavior of one of the biggest mysteries of our time, the accelerating expansion of the universe. And to this day, modern theories on dark energy actually use Einstein's cosmological constant. So it really wasn't a blunder at all to create, or rather to include this constant in his work. So we're now able to see far out into the depths of our expanding universe, and we continue seeing further and further and having a greater understanding thanks to new developments in technology. For example, we now have the Hubble Space Telescope, named in honor of the astronomer who expanded our view of the universe. In 2012, the Hubble telescope finished a 10-year-long project of collecting light from the same tiny patch of sky. So here we see the Hubble telescope, and we have our sun in the background, and here is that patch of sky. That's the Hubble Extreme Deep Field. And what Hubble did was it stared at this exact same spot, collecting light for years and years, to just see deeper and deeper out into this small area just below the Fornax constellation. So if we zoom in here, we can actually take a closer look at what Hubble discovered through its 10-year-long mission. This is the Hubble Extreme Deep Field. Every speck of light in this image, except for the ones you see with spikes, those are actually stars in the field of view, but every other speck is its own very galaxy. So see up here, I'm circling in red, that's an example of one of our stars that was in the front of this view, but it looked so far out that we have all these different galaxies. You can even see some of the spirals happening with these galaxies in this field. So this really just shook our understanding of how many galaxies are out there, because we know each of these specks has billions upon billions of stars of its own. And in fact, there are about 15,000 galaxies in this tiny patch of sky alone. So you can just imagine this density of galaxies distributed all across our celestial sphere. So we now have an improved understanding of just how much is out there in our universe. But we still need to know how it got there. How did the universe become what it is today? To answer these questions, we need to look to the mid-1960s, when radio astronomers Robert Wilson and Arno Penzias accidentally discovered the oldest light in the universe, light left over from the very earliest stages of our universe's formation. So Wilson and Penzias were not looking to do this at all. They weren't trying to do anything profound. In fact, we were just working for AT&T to improve long-distance phone calls. They were working at the Bell Lab in New Jersey, which housed this giant radio antenna. So they were just working with this antenna to improve phone calls and supposed to be working in what was called a quiet part of the sky, meaning they weren't supposed to pick up any background noise. But what they found was this part of the sky wasn't so quiet after all. They continuously detected a steady hiss. They racked their brains for months trying to figure out the source of this signal. They marked off everything, from the local Army radar base to cars traveling by on the Garden State Parkway. They even thought it was from pigeon poop on the antenna. They eliminated every possible source. Yes, that means they even scraped pigeon poop off the antenna and even killed some of the birds living there. These were desperate men, and yet the background hiss still remained. Coincidentally, around the same time, astronomers had been searching for the predicted background radiation from the Big Bang. The Big Bang is the theory that everything in our universe started about 13.8 billion years ago as an infinitely small and infinitely dense point known as a singularity, and then it continuously expanded and evolved to form the inflating cosmos that we live in today. A common misunderstanding about the Big Bang Theory is that it tells the story of the universe's creation. In reality, we have no idea how that singularity got there, how that infinitely hot and infinitely dense initial point was initiated. What the Big Bang Theory does do is tell us what happened after that. It describes the expansion and continuous inflation that caused the cosmos to go from that mysterious singularity to its still mysterious modern-day self. Ever since Hubble's discovery, people have been trying to figure out, what might exist still from this expanding universe. What would be the implications of this Big Bang Theory, and what would be left? One thing that we know would be that there is leftover light from this early formation. And so at the time, astronomers were looking for this light, and they were trying to find what was left over. And little did they know that two wildly confused scientists at Bell's lab, working simply for AT&T, had accidentally discovered these pesky photons from the past. So here we see what they really discovered. This is the cosmic microwave background. So Wilson and Penzias accidentally discovered this CMB, cosmic microwave background radiation. So that's what's pictured here. So this is really just a map of temperature variations in the early universe. So despite the fact that these fluctuations are extraordinarily small, we have them to thank to the formation of our universe structure. The red areas you see here indicate places with very slightly higher temperatures and higher densities, whereas the blue areas show where in the universe it was slightly cooler, just enough so that atoms in our early universe were drawn towards the red areas, which went on to form the seeds of galaxies that we have today. Along with these temperature variations, we also had density fluctuations, and there were pressure waves that can manifest themselves through sound. So the sound we're talking about can actually be converted into the audible range so we can hear it. And these were just waves going through our early universe that we can actually listen to and convert into the range our ear is able to perceive. Let's take a listen. That buzz you heard was the sound of the cosmic microwave background, and what they did was they sonified it, meaning we audibilized that data so that we could actually understand it and listen to these variations and these sound waves with the ear. So all of these discoveries are really revolutionizing our understanding of how massive our universe is. But this newfound information continues to beg the question, if our universe is really so extensive, so expansive, can we really be alone in it? Is there other life out there? In order to answer these questions, in 2009, NASA launches the Kepler Space Telescope. Named after Johannes Kepler, Tycho Brahe's prodigy. The Kepler telescope, seen here, was tasked with the mission to discover planets that may hold the answer to extraterrestrial life. So what it does is it looks for planets just like our own Earth that reside in what we call the habitable zones of their host stars. So what that means is they're in an area around the star that they're orbiting that's not too cold and not too hot for life to exist. We also call these Goldilocks zones. The area that Kepler focused on was it's called its field of view. It was a small piece of sky located near the constellation Cygnus the Swan, depicted here in red. Today, Kepler has discovered nearly 5,000 exoplanets in this area. So its search area is right here in red, and we know that there are over 5,000 exoplanet candidates. And in addition to that, we actually have 33 of these planets confirmed to be within the habitable zone. That's what we're seeing here in green. While 33 seems like a small number, remember that this is a small piece of sky, right? So when we look at the statistics of this, it actually shows that there could be as many as 40 billion planets in a habitable zone just in our own Milky Way galaxy, just where our galaxy is. So 40 billion planets could have the potential to support life as we know it in our very own galaxy. This realization left astronomers amazed, and this astonishment just keeps on moving. More recently, astronomers and physicists have been awestruck by the recent discovery of gravitational waves, yet another phenomenon predicted by Einstein's theory of relativity. Gravitational waves are ripples in the fabric of space-time, the very same space-time we looked at earlier with our yellow nylon. These ripples are caused by two objects orbiting each other, and this can actually be any two objects. So you could go home and create gravitational waves of your very own. Just grab a friend and start running circles around each other, and you would actually be creating your own ripples in space-time. It's just that these gravitational waves, these ripples you'd be creating, are so small that we can't detect these distortions. So we need to look to bigger and bigger objects such as black holes. And this is exactly what the LIGO experiment has done. So here we see two large black holes simulated orbiting one another. In LIGO, the Laser Interferometer Gravitational Wave Observatory was looking for a signal from two black holes about to collide, because right before they collide, they orbit around each other very, very quickly, faster and faster, creating strong distortions in space-time that we know to be gravitational waves. So that's what we found, and that's what we've been looking for years and years. This here we see is LIGO. There are two very large detectors, one in Louisiana on the left and the other in Washington State. These detectors are literally looking for the distortions in space-time, and we need two of them to confirm that if one sees something, it was a true detection and not just, say, from a truck traveling by. So if they both detect the exact same signal, we know that it's not coincidence and it's not accident, but it really is a true detection. So these black hole mergers, like the one we saw simulated earlier, are happening all the time. But the reason we didn't see this ripple effect until recently is because the distortion that they cause that needs to be detected is on the order of 1/10,000th the diameter of a proton. That's like noticing a change as small as a soccer ball in something the size of our Milky Way. And remember, our Milky Way takes about 100,000 light years. That means it takes light itself about 100,000 years to go across our galaxy. And we'd be looking for a soccer ball-sized change. So as we've seen, the cosmos is rich with these mysteries and wonders that astronomers get to continuously explore. And I personally believe that just as important as these awe-inspiring discoveries is the public's access to them. Everyone deserves to know and understand the universe in which we live, and it's important to include all audiences in this process of discovery. This is one of the reasons worldwide efforts are currently underway to 3D print our universe, so we can make astronomy more available for those who are blind or visually impaired. For example, we're creating tactile models of objects, such as the moon, which is what you see here. So we can 3D print the moon, we can 3D print satellites, and we can create tactile ways to understand our universe. And this is a really important way to improve science accessibility. Another way to work on this is through sound. So earlier, we listened to the cosmic microwave background using sonification, which again is when we're now audibilizing data, meaning we're converting it into sound so we can understand it with the ear. This sonification is extremely interesting because it doesn't just make science more accessible, but it actually helps us discover completely new things. So, for example, we can actually listen to the different bursts of plasma that come off the sun. So what you just heard there was an example of sonification when we're listening to a coronal mass ejection. Now, a coronal mass ejection, or CME, is a huge burst of plasma that gets shot off the sun in an eruption. So this plasma bubble, if you will, can contain billions of tons of matter from the sun, and it propagates out through our entire solar system. So this big plasma bubble is called a coronal mass ejection, and we can actually see it moving out here. So there we have our small sun in the center, and we could hear behind me, again, that sound of the coronal mass ejection propagating through our solar system. So, as we've seen, during the thousands of years of exploration, we've learned so much. We've built this foundation of knowledge and created beautiful maps, executed these systematic searches, and continued to push the boundaries of our understanding of our universe. People deserve to know that not only is there room for you in science and astronomy, there is a need for you, and there is still so much more to learn. I hope you can leave here tonight feeling curious and excited about the search for knowledge and the search for discovery, and I hope you know that you can be a part of it. Thank you all so much for coming, and I hope you have a great rest of your night.